All right, welcome everyone to our second talk of today, which is our last AWM student seminar for the semester. We are welcoming Indulekha from Carnegie Mellon University, who will be speaking to us about motion of elastic thin films, a variational approach. So thank you very much.
Hello everyone, I am Indulekha. I am a fourth year PhD student in the Department of Mathematics at Carnegie Mellon University. And today I'm going to talk about elastic thin films, which is an important arena of material science with a rich mathematical theory background. In this talk, I would like to give a basic overview of the mathematical model and give an idea of where my work fits in this big picture. So I would give an introduction of the physical problem and then the mathematical problem, and then talk about a bit of the mathematical theory involved in the model. So elastic thin films has a lot of applications as clear from the picture in this slide. It's an umbrella term used in a wide variety of fields, and depending on the application, the materials involved and the manufacturing process changes, and so does the mathematical model. The basic model is that we are trying to grow a thin film, like a layer of small thickness on a solid substrate. And it could be a protective layer on a knee implant, or a protective layer on a heat engine, or it could be a semiconductor, like a part of a semiconductor. It can be many things, but most basically it is a thin film, a solid film on a solid substrate. There are many factors that affect the manufacturing process, which are the interfacial interaction of the film and substrate material, and the elastic stress and displacement within the film, along with environmental factors like temperature. The film formation depends on, or the equilibrium configuration of the film, or the movement of film towards equilibrium. It depends on the minimization of interfacial surface energy and elastic energy, as all physical systems. And this is where calculus of variations come in, because calculus of variations is about minimizing or optimizing energy in physical systems. The growth of thin film problem uh, can be divided into, or looked at as wetting, diwetting, or void problems, depending on the morphology of the film material. I mean, morphology of the film on the substrate. And in the wetting regime, the film material kind of spreads on the substrate. Whereas in the de-wetting regime, they form islands with sharp corners. And in material, when we talk about material defects, we are talking about voids within the film and how those affect the morphology of the film. And these three problems are analyzed differently, and they present their own challenges. The initial mathematical studies were focused on figuring out the equilibrium configuration of the film on substrate, depending on minimization of surface and elastic energy. And later, the theory was developed to take care of the movement of the elastic thin films on the substrate during the manufacturing process. My work is about the motion of elastic thin film islands in the de-wetting regime, and it's a two-dimensional model. And I consider the film growth due to condensation of film vapor into solid film. That is the way in which the film is manufactured, or like that is what we consider to be the most relevant physical factor in the manufacturing of the film. Now let's go to the mathematical problem statement. Well, this is a toy model picture of the film island formation. And if we imagine taking a cross section of one of those film islands and look at the parameters of the contact points alpha and beta, the island height h, and the elastic displacement within the film u, we get an idea of the dynamics of the film depending on these four parameters. And the substrate is, of course, modeled as r cross 0 negative infinity, the lower half of the plane. For a given time t, we have the endpoints alpha and beta, like they move in time. H is the height of the island film above the substrate. Omega h is the subgraph of h, which is the area under h. Uh, I mean, yeah, the elastic displacement within the film U is a function from omega h to R2, and film boundary is denoted by capital gamma h, which is the graph of the function h. The energy of this system uh, depends on like the interfacial surface energy and the elastic energy. Surface energy has the form detailed on the slide. Like if kappa is the curvature of the graph gamma h, gamma fv, gamma vs, and gamma fs represent the surface energy densities between film and vapor, vapor and substrate, and film and substrate, and nu naught is a small parameter. Then the surface energy is has this given form. Like these are taken from literature, and I would like to note that the nu naught over 2 integral of curvature square is in fact a mathematical tool, a regularizing tool that helps to smoothen the curves of H in some way. It makes the analysis easier, and it is uh, kind of like in many problems, like it's an open problem that analysis, if analysis can be done without this term. The elastic energy has this specific form. This is called as this is a linearized in a elastic energy of materials where lambda and mu are called Lamé constants that depend on the materials. And W of psi, the elastic energy, has the property that it is bounded above and below by the norm of psi square, where here psi denotes the symmetric gradient of U, the elastic displacement. And elastic energy is the integral of W over omega h. So at every point of time, there is minimization of surface and elastic energy that determines the form of the film, the shape of the film. But then the film changes or moves depending on the way manufacturing happens, depending on the dominant, let's say, the dominant factor in manufacturing, in the manufacturing process. we look at the evolution of this system as a gradient flow, and where gradient flow is the equation denoted by equation 3, uh, the theory goes like this. If H is a Hilbert space and D is a subset of an open subset of H, we have an energy functional psi from D to R, and T is denotes time, which is greater than 0. If we want to evolve a function H from 0t to D such that psi of H decreases in time, we consider this evolution equation, which is called as the gradient flow. Here, our system depends on minimization of surface and elastic energy. So we would look at, or like in this problem, psi is kind of the sum of elastic and surface energies. And we are looking at the evolution of our system. And that evolution depends on uh, the manufacturing process, as I said. That means that the partial differential equation changes in every case. The way we analyze the gradient flow is uh, the minimizing moments method. It's an implicit in time scheme credited to Ennio de Giorgi. So what happens is that for given an initial value of, like, say, alpha, beta, and H and U, we fix a time step, like, and define an incremental minimization problem depending on that time step that would give us alpha, beta, H, and U at a later time point by minimization of an energy that is dependent on tau, the time step. So if we continue to do that, we would be able to obtain approximate solutions at discrete time points. But then we can interpolate these these points or these approximate solutions that we get in time. We can do the interpolation in time to have time dependent functions. But these time dependent functions would still be uh, dis the time dependent functions are not accurate because we only have information about discrete time points. And hence these solutions will depend on the time step that we fix. But then we can take these time step to 0 if we have estimates on, like, regularity estimates on dependent on the fixed time step. And we can ensure that these, as the time step converges to 0, the solutions converge in a relevant space. And that solution will be the solution of our PD. So the bulk of the work is in finding the existence of approximate minimizers at every discrete time step and finding estimates and bounds that can help us finding the appropriate convergence. So the setting would be that we need a space and an energy functional and an incremental minimization term, a penalization term that leads to the LHS of the gradient flow. The LHS being the time derivative of H in this case. So our incremental minimization problem goes like this. We define an energy term that depends on the initial condition alpha naught, beta naught, and H naught, and obtain an energy, a total energy term, which is the sum of the surface energy, the elastic energy, and the incremental minimization term. So given alpha naught, beta naught, h naught, we find the minimizers alpha, beta, h after time tau. So once we have alpha, beta, h, depending on them, we can define, say, f1 of alpha, beta, h, and u and find the minimizer at a later stage. So this is the process that I was talking about in the previous slide. And what we do is that after figuring out approximate minimizers and interpolating them, we take tau to 0 and find the convergence. Another major factor in the analysis of this problem is the analysis of the elastic displacement boundary value problem. So, since due to the special form of the elastic energy, the elastic displacement U is a solution of an elliptic boundary value problem with mixed Riemann, mixed Neumann and Dirichlet boundary values. And we are finding or solving the elliptic boundary value problem in a domain with corners, which is also moving in time. So that is a major challenge in analyzing this problem. We need estimates on the regularity of U at every discrete time point. Not just U, but also the value, also trace of U. That is, of course, dependent on the regularity of U in the bulk of omega H. All of these turn out to be crucial in carrying out the minimizing moment scheme that we talked about in the previous slide. So to analyze the corners of omega H, what we in fact do is to transform the corner to a triangle uh, using a diffeomorphism and then analyze the equivalent elliptic boundary value problem in the triangle, use the elliptic regularity results already known in domains like this, and then transform everything back to obtain regularity of U in the actual domain. Sorry. So the challenge, of course, again, is that the domain and the boundary value problem both change in time. So we need to account for that and find appropriate estimates to make the convergence, the final convergence as tau goes to 0 easier. So to conclude, I just talk about the differential equations that govern the system, the differential equations that give the dynamics of alpha, beta, H, and U. So the notation that I have followed here is that dot denotes time derivative and prime denotes the space derivative. Alpha and beta move according to the differential equation described over here. They are both time dependent functions, and like we can of course also prove that they have a fixed gap between them. Alpha beta of t minus alpha of t has a lower bound. This equation represents the dynamics of H. It is fourth order in time, fourth order in space. And the minimization associated with H, or like the minimization of surface energy and elastic energy, are subject to the constraint that the area under the graph of H is a constant in time. And because of that, we have a Lagrange multiplier at every time point t. Lagrange multiplier, which is a constant for a given time point. And W bar is the value of the elastic energy term on the graph of H. And this is the elliptic PDE that governs the the dynamics and the nature of U, the elastic displacement. The Neumann boundary condition is the natural condition, and the Dirichlet condition is uh, it comes from the physical system that it is attached to the substrate in a specific way, and it is the Dirichlet condition that kind of leads to elastic strain in the first place. Moving forward, we would like to analyze the system without the curvature regularization term, the smoothening term in surface energy that I was talking about, in both wetting and dewetting regimes. In the work that I was talking about, we had the existence of solution only in a short time interval, 0 to t, and t dependent on the parameters of the system. But we would like to study the existence of solution in 0 infinity. And of course, we have been working only on a two-dimensional model on the cross-section of islands. The three-dimensional models uh, could be harder to analyze because, like the corners or uh, the curvature terms, like deciding on what curvature to look at, like that can be complicated. The analysis can be complicated, but we would like to look at that sometime. And another way is another thing to look at is the numerical analysis of the model, like the, and how well it relates to the physical systems that we uh, try to model. I would like to acknowledge the support of my PhD advisor, Professor Giovanni Leoni, and Professor Irene Fonseca for her valuable comments on the work. And I would also like to thank Simmons Foundation for their funding. Thanks a lot for listening, and I would like to hear your questions.
All right, thank you very much. That was really interesting. I'm going to pause the recording before questions.